One of the things the periodic table enables us to do is to write electron configurations for each of the elements. And if you will pardon the bad poetry, each orbital in an atom on the ones that come before builds. All orbitals are there all the time waiting to be filled. The orbitals are regions of space that electrons may occupy, and they're there even if there's no electron occupying them. Here is the fundamental orbital, the 1s orbital. Every atom has them. We're going to show more or less the easy one. It was hydrogen. Hydrogen has all the orbitals, even though its ground state orbital is the 1s. Outside that, and larger in dimensions, is the 2s orbital. All of these pictures are of equal probability surfaces. They aren't solid spheres like Bohr had it. They're more like mosquito graphs, but we have shown the solid as a place where each point has the same probability as the others. And since this is spherically symmetrical, you will see something that looks very much like a sphere. So the 2s orbital is their higher energy level. Also on the second energy level are three 2p orbitals along the x, the y, and the z axis. And they will each, as all orbitals do, hold 2 electrons. So that on the second energy level, there are 2 kinds of orbitals, s and p, and they can each orbital hold 2 electrons. Outside that, the 3s orbital, there are 3 kinds of orbitals on the third energy level. And the 3s is there, the 3pz, the 3px, and the 3py. On the third energy level, there is also a set of d orbitals, but we'll wait for a little bit to talk about those. Now, filling orbitals. We always add electrons to the lowest energy orbital that isn't already filled. So this is called the Aufbau Principle, lowest energy first. We never put more than 2 electrons into an orbital. That's the exclusion principle. And when there are more than one degenerate orbital available, as on the p's or the d's, we always half fill each orbital before we completely fill any of them. We start with hydrogen. All its compounds suggest that the atom bonds only one time, and it has an atomic mass of 1. It means it has only 1 electrons because it has only 1 proton. The lowest energy orbital is the 1s, and in the ground state, the hydrogen atom is there. When we draw the box, we have 1 electron, which is an up arrow. We show it here. It could have been a down arrow, but it really doesn't matter. But 1 electron, and we call that 1s. That's because on the first energy level and is an s orbital, and there's only 1 electron in it. Helium is the first noble gas. Experiment shows it does not react, so the 1s orbital, which gets its second electron, must be full. 2 electrons fill up the 1s orbital. This is the electron configuration for helium. The box shows 2 electrons, and it's 1s with 2 electrons in it. Now, we fill our periodic table from left to right and top to bottom. We have offset hydrogen and helium from the rest of the elements to show this. They're characterized by s electrons. Everything on the left 2 columns is characterized by an s electron. On the far right, because every time we have p orbitals, we have 3 of them, we have 6 spaces in each period, and they're all characterized by p electrons. In the center, we have the d block, 10 atoms wide, and then on the bottom we have the F block. We're not going to talk about that much. So let's look at the second period. Beginning on the left, we have lithium. Lithium has 3 electrons. The first energy level is full with 2, and then we have an s electron, an s orbital with 1 electron, also the lithium. It builds on the noble gas configuration of helium, so we add the 1 2s electron. With beryllium, we add a second s electron, and now the 2s is full. With boron, we have to skip to the right because only s and p orbitals are on the second energy level. So we add an electron to the next available orbital, which is 2px. And then, following Hund's rule, we add, for carbon, we add an electron to the next orbital, the 2py. And finally, with nitrogen, we add 1 electron to the 2pz. So as you can see on the bottom of the screen, we don't say px, py, pz. That takes up too much space. We just say 2p with 3 electrons, 1 in each of the 2p orbitals. Now that we have half filled, we can completely fill the first 2p orbital with another electron for oxygen, which has a total of 8. Then fluorine has 5 2p electrons in it, and you'll notice there's just 1 available slot left, and with neon, 10 electrons, we fill that, and now the second energy level is full with complete s and p orbitals, and it's a very low energy situation. Experiment tells us that neon is non-reactive, stable, and low energy. We can speak now of the neon core. Since that neon core is low energy, it is the dickens to get any electrons away from it. And so we essentially say, that's done. Any electrons above that may come off, but none of these electrons will come off. We call that the neon core. Sodium has the neon core to build on. It's got 1 more electron. That's all it has that is going to react. And so that's why it loses 1 electron in chemical reactions. That's the electron. By losing the single 3s electron, it attains that very low energy noble gas configuration of neon, 10 electrons. Now, if we have a sodium ion, it has lost the electron. The neon core is still there and will not change. But now we're at 3s0, and we are in a low energy, non-reactive state. Now, sodium has a shortcut to an electron configuration. Since nothing's going to come away from the neon core, we use that as a shortcut notation, and we can give only it and the valence electron, and that tells us it's sodium. So this is how we can show sodium. We put the core in brackets, and the only thing you can put in there is a noble gas, because that's the only kind of core there is, something that will not lose any electrons. And then we just show the outer shell electron, we'll call that a valence electron, right on top of it. So the 3s1 is characteristic of sodium. Magnesium has 2 electrons beyond the neon core, so here is the shortcut way of doing it. Aluminum has 3. Now we're into the p block on the 3rd energy level. Put the core in brackets and show the outer shell electrons. The outer shell electrons are 3, 3s2 and 3p1. Show that without showing all the 10 electrons in their longhand state. And then we can move all the way over to chlorine. So we add 1 electron each time, and chlorine needs 1 electron to look like a noble gas. That explains what we'll see as its high electronegativity. Argon then is the next one, and now we have another noble gas core. It is the noble gas core that is going to be used for the elements that come after it. Potassium then has an argon core. So we put the core in brackets and show the outer shell electrons on top. With calcium, we have 2 outer shell electrons. With scandium, 3. Now, just as in Aufbau, this next electron, the characteristic scandium electron, and all of the rest of this D block will be characterized by 3D electrons. And we did this because the 4s is slightly lower in energy than the 3D orbitals. So once we have filled the 4s with the 2 electrons, then we add a 3rd electron for scandium. And from that point, the 4th period transition metals add 1 3D electron with each new element. So titanium is characterized 3D2. When we get to zinc, we have filled the 3D orbitals, and it is going to have the argon core with the 4s2 electrons and 10 3D electrons. Now, this is particularly low energy, and so when zinc reacts, it's going to get rid of these 2 4s electrons, which are by now higher in energy than any of the Ds. With 1 more electron, gallium's configuration, we begin to add to the 4p orbitals, so 1 for gallium, and so forth. Now it's your turn. Write electron configurations and box or orbital diagrams for these elements. Go ahead and turn off the recorder, and then you can check your work when you turn it back on. Vanadium, 4s2 3d3 on top of the argon core. Copper, 4s2 3d9 on top of the argon core. Rubidium now has a krypton core and 5s1. Chromium can either be written with an argon core, 4s2 3d4, and it actually turns out that slightly lower energy argon with 4s1 and 3d5, so that the chromium actually has multiple valences. Nickel, 4s2 3d8 on top of the argon core. Germanium, 4s2 3d10 4p2 on top of the argon core. And bromine, just like chlorine, it has the p5 configuration on the 4th energy level. Now watch these tutorials and take notes. The first video is on electron configuration. The second video is on the rules governing how electrons fill. The third is on what the orbitals look like. And the fourth is a review of the scientists who helped come up with modern atomic theory and why electrons do what they do.